Hello, this is video 29. In this video, we're finally going to introduce friction, so we'll be able to do Newton's second law problems, and we're not going to have to ignore friction. In particular, we're going to talk about kinetic friction. So first, we need to talk about friction in general. So friction is a force that opposes motion or attempted motion. In this video, we're going to talk about the first definition, that it opposes motion. It's partly due to the roughness of the surfaces in contact. You can see in this picture when surfaces are rough, that provides some resistance to the motion. And it's also due to the attractive forces between the molecules, those molecular forces that attract each other, that's also going to provide some resistance. So now specifically, kinetic friction is friction that acts when an object is moving. So it's given by this expression here, Fk equals mu k times n is the normal force, and mu k is the coefficient of kinetic friction. So this is a property of the surface. So the higher the coefficient, the more rough that surface is, and the more friction there's going to be. So friction is a force, its direction will be parallel to the surface and opposite the motion. So in this picture, you have a force pushing the trash can to the right, so the friction force is going to be to the left. So the unit is newtons, and it is a vector like all forces. Let's do an example. So this one I chose because it's an applet, so you can feel free to click on the link and play with it a little bit. I encourage you to play with it first before you look at my solution. So in this case, we're given that the box is moving, and we're given the coefficient of kinetic friction is 0.3, the mass is 100 kilogram, and g is going to be 10 meters per second squared instead of 9.8, just to make calculations easier. How much force is needed to keep the box moving? So we know that the box can move at a constant velocity if this applied force, it balances the friction force. If they're equal, it can still move. So really, what we just need to do is find that friction force. So using the definition, mu k times n, and in this case, the normal force balances the weight. So the normal force is equal to the weight. There are no other vertical forces. So for this case, we can write mu k mg, and then we multiply 0.3 times 100 times 10, and we'll get 300 newtons. Now if you do play with the simulation, you'll see that if the box is at rest to begin with, that this 300 Newton is not going to get the box moving. That's going to have to do with a different type of friction that we'll talk about in the next video. So let's do your turn, and then we'll have one more example. I wanted to do an example with an object on an incline. So the first step is to figure out, well, what's the free body diagram? From now on, we're going to assume that there's friction unless the problem specifically tells us that there's no friction. So let's see. We know that it can't be D because weight always has to go straight down. And we know that when an object is on a surface, there's a normal force perpendicular. So E here is missing a normal force. So we're going to assume there's friction, and it's going to oppose the motion, so it's going to go to the left here. So A is missing friction, and so is B. So the best choice is C, where this force to the left is the kinetic friction, and this is normal force, and this is the weight going straight down. So now that we have the free body diagram, we can do an example. So I'll go ahead and redraw that free body diagram. Again, we're not supposed to put the surface, but when there's an incline, I like to put a surface. It helps me draw all the forces. So let's take a look at this example. A car is sliding down the icy driveway. We're given an angle of 20 degrees here. Determine the acceleration of the car. The driveway has a coefficient of kinetic friction of 0.2. So it's a small coefficient because it's icy, but there's still some friction. So we know that when there's forces, it's most likely going to be a Newton's second law problem. So we separate the x and the y directions. We're going to write Newton's second law separately in both directions. The sum of the forces equals ma separately in x and y. And then in our free body diagram here, we need to identify our coordinate system, and we've talked about in a previous video that we like to rotate the coordinate system so that the direction along the incline is the x direction and perpendicular is the y direction. And now we see that the weight is the only diagonal force in this rotated coordinate system, so we can draw the components. When you draw the components, make sure that the y component is perpendicular to the surface and the x component is parallel to the surface. So I call this wy and wx, where mg here is w. So we're pretty much good to go here. We know that it's going to accelerate down the incline here, and I like to make the direction of the acceleration a positive direction. So now let's sum up all the forces that we drew that were going in the x direction. We drew wx and friction to the left, so friction is negative. And I'll say that's equal to ma because that's the only acceleration. And then I'm going to substitute these forces for what I know about them. I know that wx is that x component of the force. It's opposite the angle. We've mentioned that this given angle of 20 degrees is the same one as this little angle right here. So we can substitute mg sine of theta. And in the friction force, we're going to substitute in the definition, which is the coefficient of kinetic friction times the normal force. So all of that's equal to ma, and now we're kind of stuck. We don't know normal force, we don't know the mass. Let's move on to the y direction. The y direction, we have the normal force upward and wy going down, which is negative. And in the y direction, right, this is perpendicular to the incline here. The car is not jumping up and down. We're in equilibrium. There are no forces, no net force. So let's substitute what we know for each force. Do not substitute mg for n. N is not equal to mg. We'll see that n is actually equal to wy. wy is going to be mg cosine theta, since that component is adjacent to the angle. So now we can solve for the normal force. And this is very typical when you have friction in a problem. You're going to solve for the normal force in the y direction, and then you're going to plug that in the x direction. So let's do just that. So we have mg sine theta minus mu k times mg cosine theta equals ma. So maybe you were kind of perplexed before because we were not given the mass. But this is a general idea. If you're not given the mass in a problem, that means it's probably going to cancel out at some point. And you can see that the mass is in every single term. So we can just divide every term by the mass. The mass cancels out. So now we have solved for the acceleration. I'll rewrite it so it's nice and neat. But the acceleration is g sine theta minus mu times g cosine theta. So go ahead and plug in everything. 9.8 for g, sine of 20 degrees, minus 0.2 times 9.8 times cosine of 20 degrees. When you plug all of that in, you get 1.51 meters per second squared. So that's all for this video. So we talked about friction and we applied it in a Newton's second law problem. So when there's friction, you know how to draw. It's always opposite the motion, parallel to the surface. And then you just have that extra step of having to find that normal force before you can plug it into that definition of friction. Don't just say a normal force is equal to mg.